Two stars, already dead, locked in orbit around each other. Not burning, not shining like normal stars, but collapsing. Neutron stars are what remain after massive stars die, objects so dense that a single teaspoon of their material would weigh billions of tons. And when two of them meet, they don't just collide, they spiral, faster, closer, tighter, until space itself begins to shake. Invisible waves ripple outward, stretching and compressing the universe itself. And then, in a fraction of a second, everything ends. A collision so violent, it forges elements heavier than anything inside normal stars. Gold, platinum, matter created in an instant and thrown across the cosmos. A flash brighter than entire galaxies. A burst of energy that can be detected across millions of light years. This is not just an explosion. It is one of the most powerful events in the universe. A moment where gravity, energy, and matter all reach their absolute limits. But what actually happens in that final second before impact? What do these stars become when they merge? And how can something so destructive be responsible for creating the very elements we find here on Earth? Because when neutron stars collide, they don't just destroy, they create. If you enjoy calm, cinematic journeys into the most extreme events in the universe, subscribe to Theories Before Sleep, because what happens next goes far beyond anything we can imagine. Long before the collision, long before the light, long before the explosion that can outshine entire galaxies, there are two objects, not stars in the way we usually imagine them. They do not burn, they do not shine because of fusion. They are what remains after everything else is gone. Neutron stars are the collapsed cores of massive stars that ended their lives in supernova explosions. When a star far larger than our Sun runs out of fuel, it can no longer support itself against its own gravity. The outer layers are blown away in a violent explosion, but the core does not disappear. Instead, it collapses inward under unimaginable pressure, compressing matter to a state that does not exist anywhere else in the universe. What remains is something incredibly small, yet incredibly massive. A neutron star is typically only about 20 kilometers across, roughly the size of a city, and yet it contains more mass than the Sun. This means that all that mass has been compressed into an incredibly small volume, creating densities so extreme that normal matter cannot survive in its original form. Atoms are destroyed, electrons are forced into protons, everything collapses into neutrons. And this is where the name comes from. But even that description barely captures the reality. Because a neutron star is not just dense, it is one of the densest objects that can exist without collapsing into a black hole. To understand just how extreme this is, imagine taking the mass of an entire star and compressing it into something smaller than a city. The gravitational pull at the surface becomes enormous. Time itself slows down slightly. Light bends. Space is curved in ways that are difficult to visualize. And yet, these objects are stable. They exist. And sometimes, they are not alone. In some regions of the universe, two neutron stars can form together. This usually happens when two massive stars are born as a binary system. They live their lives orbiting each other, evolving together, and eventually, both of them end in supernova explosions. What remains are two neutron stars, still bound by gravity, continuing their orbit. At first, nothing dramatic happens. They circle each other slowly, calmly, separated by a distance that allows them to remain stable for millions, even billions of years. But even in this calm state, something is already happening. Every time they orbit, they lose energy. Not through light, not through radiation in the way normal stars do, but through something far more subtle. Gravitational waves. These are ripples in space-time itself. As the two neutron stars move, they disturb the fabric of space around them, sending out waves that travel outward at the speed of light. These waves carry energy away from the system, and as energy is lost, the orbit changes. Very slowly at first, the stars move closer together. The distance between them decreases. Their orbital speed increases. And this process continues over immense periods of time. From the outside, nothing seems urgent, nothing seems dramatic. But the system is evolving, and it is moving towards something inevitable. Because as the stars get closer, the rate of energy loss increases. The gravitational waves become stronger. The inward spiral accelerates. What once took millions of years now takes thousands, then hundreds, then less. The system begins to change more rapidly. The neutron stars are no longer distant companions. They are approaching each other. Their gravitational interaction becomes stronger. Their shapes begin to distort slightly. Not dramatically, but enough. Because at this scale, even small changes matter. The intense gravity of each star begins to pull on the other, creating tidal forces. Just as the moon creates tides on Earth, these neutron stars begin to stretch each other slightly. But unlike Earth, these are objects of incredible density. They resist deformation. And yet, under enough force, even they begin to respond. Their surfaces shift. Their internal structure reacts. And something else becomes important. Magnetic fields. Neutron stars often have extremely strong magnetic fields, trillions of times stronger than Earth's. As they move closer together, these magnetic fields begin to interact, twisting and reconnecting in complex ways. Energy builds. Not just gravitational, not just kinetic, but electromagnetic. All of these forces are building toward a single moment. But that moment is still far away, because even as the spiral accelerates, it is still gradual, still controlled, still predictable, until it isn't. Because there comes a point where everything changes. A threshold, where the distance between the stars becomes so small that the final phase begins. The inspiral. At this stage, the motion is no longer slow. The stars orbit each other faster and faster. Their speed increases dramatically. They can complete an orbit in seconds, then milliseconds. The gravitational waves they emit become incredibly strong, forming a signal that can be detected across vast distances in the universe. This is how we first confirmed their existence, not by seeing them, but by listening, detecting the ripples they create in space-time. And those ripples tell a story of two objects falling toward each other, not in a straight line, but in a tightening spiral, each orbit bringing them closer, each moment increasing the intensity, until finally there is no more space left between them. But that moment is not what we think, because the collision is not instant. It is not a simple impact. It is a process, a final sequence of events that unfolds in fractions of a second, but contains more energy than we can easily comprehend. And to understand that moment, we need to go deeper into what happens as these two neutron stars reach the end of their journey, because the collision itself is only the beginning. What happens next is where everything changes. There is a moment, just before impact, when everything accelerates, not gradually, not predictably, but suddenly. The slow spiral that once took millions of years compresses into seconds. The distance between the two neutron stars shrinks with every orbit, and each orbit now happens faster than the last. What once was calm and distant becomes intense and unavoidable. The stars are no longer companions. They are no longer separate systems. They are a single event, unfolding. At this stage, the motion becomes extreme. The two neutron stars orbit each other at a significant fraction of the speed of light. Their velocities are so high that space itself cannot remain unaffected. The fabric of space-time is dragged, stretched, and twisted by their motion. Gravitational waves surge outward, stronger than ever before. If we could listen to them, we would hear something unusual, a rising tone, a rapid increase in frequency and intensity, a sound that starts low and grows higher and higher, a chirp. That chirp is not just a signal, it is a countdown. Because each oscillation represents another orbit, each peak represents another loss of energy. And each loss of energy brings the stars closer together. The spiral tightens, the motion accelerates. There is no escape. At this distance, gravity is no longer just a force pulling objects together. It becomes a dominant structure, shaping everything around it. Even light cannot travel in straight lines near these objects. It bends, curves, and distorts as it passes through the intense gravitational field. And then, something else begins to happen. The stars deform. Neutron stars are incredibly rigid. Their structure resists change more than almost anything else in the universe. But at this level of gravitational interaction, even that rigidity begins to fail. Each star starts to stretch slightly. Not dramatically at first, but enough to matter. Tidal forces pull material outward, creating subtle distortions in their shape. The surfaces are no longer perfectly spherical. They become elongated, pulled toward each other by the immense gravitational attraction. This is the beginning of contact. Not physical contact yet, but structural interaction. The outer layers respond. The internal pressure adjusts. And as this happens, the energy within the system increases, not just in motion, but in form. Because the closer the stars get, the more their gravitational fields overlap. The distinction between the two objects begins to blur, not visually, but physically. Their individual identities start to merge into a shared gravitational system. And at the same time, their magnetic fields collide. Neutron stars are often magnetars, with magnetic fields so strong they can strip atoms apart. As these fields interact, they twist and reconnect, releasing bursts of electromagnetic energy. This adds another layer to the event. Not just gravity, not just motion, but energy being released in multiple forms at once. The system becomes unstable, but not chaotic. It is still governed by the laws of physics, still following a path. But that path is narrowing, because now there is almost no space left. The stars are separated by only a few kilometers. Their surfaces are close enough that the distinction between two objects becomes almost meaningless. At this point, the final orbits happen in milliseconds. Each revolution is faster than anything we can imagine in everyday experience. The gravitational waves reach their peak. The energy output becomes enormous. And then the boundary is crossed. The surfaces touch. Not gently, not slowly, but under extreme pressure. This is not a collision like two solid objects hitting each other. It is a merging of matter under conditions that no longer resemble normal physics. The outer layers of each star begin to tear. Material is pulled away, ejected outward, at incredible speeds. Some of it escapes entirely. Some of it forms a rapidly expanding cloud, and some of it begins to swirl around the merging core. This is the beginning of the Kilonova. But the core of the event is still forming, because as the stars merge, their interiors combine. The densities increase even further, the pressure rises, and for a brief moment, something exists that may not be stable. A hypermassive object, heavier than either neutron star alone. Too massive to remain stable as a neutron star, but not yet collapsed into a black hole. This object exists for only a short time. Milliseconds, seconds at most. But during that time, it is one of the most extreme objects in the universe. Its internal structure is in constant motion. Matter is compressed, heated, and rearranged under forces we cannot fully replicate or observe directly. And around it, the explosion continues. Material ejected during the collision begins to glow. Not from heat alone, but from nuclear processes. Because the conditions created during the merger allow for something remarkable. The formation of heavy elements. Elements that cannot form in normal stars. Gold, platinum. Matter that requires extreme environments to exist. And this environment is one of the few places where it can happen. But all of this is only the beginning of the aftermath, because the fate of the merged object is not yet decided. It may collapse, or it may survive for just a little longer, and that decision depends on one thing: mass. If the combined mass exceeds a certain limit, gravity wins. The structure cannot support itself. And in that moment, everything changes again. Because what follows is not just a continuation. It is a transformation from one extreme state to another. And to understand the transformation, we need to look at what happens next. Because the collision is not the end. It is the transition into something even more powerful. The collision does not end with contact. It begins there. Because when two neutron stars finally merge, what forms in that instant is not stable. It is not balanced. It is not meant to last. The combined mass of both stars creates something that exists right at the edge of what physics allows. A hypermassive neutron star. For a fraction of time, this object resists collapse. Internal pressure, rapid rotation, and extreme energy briefly hold it together. But this balance is fragile. Every force inside it is pushing toward a single outcome. Failure. The mass is too great. The structure cannot hold. And so, almost immediately, the collapse begins. Gravity takes over completely. The core contracts further. Density increases beyond what a neutron star can support. And then, it happens. The object collapses into a black hole. Not slowly, not gradually. Instantly, the boundary forms. The event horizon appears. A region from which nothing can escape. But the formation of the black hole is not the end of the energy. It is the beginning of its release. Because the collapse does not happen in isolation. Around the newly formed black hole, a massive disk of material remains. This disk is made of the debris from the collision, matter that did not fall directly into the core, but instead began to orbit it. This accretion disk becomes one of the most energetic structures in the universe. Material spirals inward at incredible speeds. Friction heats it to extreme temperatures. Magnetic fields twist and amplify. And then, jets form. Narrow beams of energy and particles shoot outward from the poles of the black hole, moving at nearly the speed of light. These are relativistic jets, and they carry enormous amounts of energy across vast distances. If one of these jets happens to be aligned with Earth, we detect it as a gamma-ray burst, one of the most powerful signals ever observed. For a brief moment, this single event outshines entire galaxies. But the energy is not only directed into these jets. The debris cloud continues to expand. Ejected material from the collision moves outward in all directions, forming a rapidly growing shell of matter. This material is not ordinary. It has been subjected to conditions so extreme that new atomic structures begin to form. Heavy elements are created, not through the slow fusion processes of normal stars, but through rapid neutron capture, an environment where neutrons are so abundant that atomic nuclei absorb them faster than they can decay. This process builds elements heavier than iron, gold, platinum, uranium, matter that cannot form easily anywhere else. And as these newly formed elements decay and stabilize, they release energy. This energy powers the kilonova, a glowing cloud of expanding material that shines brightly for days or weeks after the collision. Its light is different from a supernova. It carries a signature that reveals the presence of a heavy element. A cosmic fingerprint, proof that this event created something new. But beyond the light, beyond the energy, beyond the explosion, there is something else. A shift in understanding, because this event is not just destructive, it is creative. It takes the remnants of dead stars and produces the building blocks of planets, of worlds, of everything we know. The gold on Earth, the metals in our technology, even elements within our own bodies, may have originated in events like this. That realization changes everything, because it means that these violent collisions are not just rare cosmic accidents. They are part of a larger cycle, a process that distributes matter across the universe, seeding galaxies with the elements needed to form new stars, new planets, and potentially life itself. But the story does not end with the explosion, because the effects of this collision continue to travel. The gravitational waves produced during the final moments spread outward, across space, across time, carrying information, a signal that can be detected from millions of light years away. This is how we first confirmed these events, not by seeing the light, but by detecting the ripples in space-time itself. In 2017, for the first time, we observed both gravitational waves and electromagnetic radiation from the same neutron star merger. This event provided direct evidence of everything we had theorized. The inspiral, the collision, the kilonova, all of it confirmed. This was not just a discovery. It was a new way of observing the universe. Because now we are not limited to light. We can listen to space itself. We can detect events that would otherwise remain invisible. And through those detections, we can reconstruct what happened, even when we cannot see it directly. But there is still something deeper in all of this. Because while we can describe the process, while we can observe the signals, while we can model the physics, there are limits. The exact conditions inside the merger, the precise behavior of matter at these densities, the full sequence of events during collapse, are still not completely understood. These are environments that push physics to its limits, where our current theories begin to strain, where new insights may still be waiting. And that is what makes neutron star collisions so important, not just because they are powerful, but because they exist at the edge of what we know. They test our understanding, they challenge our models, they reveal where our knowledge ends and where new discoveries begin. And in that sense, they are not just events. They are opportunities. Opportunities to learn more about gravity, about matter, about the fundamental structure of the universe. Because in those final moments, when two neutron stars collide, everything we understand about physics is put to the test. And what emerges is not just an explosion, but a deeper understanding of how the universe works. But even this is not the full picture, because beyond the physics, beyond the energy, beyond the creation of elements, there is a larger perspective, a perspective that connects these events to everything around us. And to understand that, we need to step back, to look not just at the collision itself, but at what it means on a cosmic scale. The collision is over in seconds, but what it creates does not stay there. Energy does not disappear. It moves. It spreads outward from the point of impact, carrying with it the signature of everything that just happened. Not as a single burst, not as a simple flash, but as multiple layers of energy traveling through space in different forms. Light, particles, waves, each one moving at its own pace, each one telling part of the story. The first to arrive are the fastest. Gamma rays. When the neutron stars collapse and the black hole forms, the jets released from the poles travel at nearly the speed of light. These jets are narrow, focused, and incredibly powerful. If one of them happens to point toward Earth, we detect a gamma ray burst. For a brief moment, this burst releases more energy than our sun will produce in its entire lifetime. And then it's gone. But that does not mean the event is over, because the gamma rays are only one layer. Behind them, something else is expanding. The kilonova, a cloud of matter thrown outward during the collision, continues to grow. This material moves at a significant fraction of the speed of light, spreading into space in all directions. At first, it is extremely hot, dense, energetic. But as it expands, it begins to cool. And as it cools, it glows. Not with the brightness of gamma rays, but with something softer, something longer lasting. Visible light, infrared. This glow carries information. It reveals what the material is made of, and what it shows is extraordinary. Heavy elements, gold, platinum, matter that was not there before the collision, matter that did not exist in those neutron stars in that form, created in seconds, and now being carried outward into the galaxy. But even this is not the end, because while light travels fast, something else moves differently. Gravitational waves. These waves are not made of energy in the same way as light. They are distortions in space-time itself. Ripples, spreading outward in all directions. Unlike light, they are not blocked by matter. They do not scatter. They do not fade easily. They pass through everything. And because of that, they carry a pure signal, a direct imprint of the motion that created them. By detecting these waves, we can reconstruct the event. The inspiral, the collision, the final collapse. All of it encoded in the pattern of those ripples. This is what makes neutron star mergers unique. They are not just visible. They are audible. Not in the way we hear sound, but in a way we can detect, measure, translate. The universe is not silent. It vibrates. And these collisions are among the loudest events it produces. But there is another layer, one that takes longer to appear. As the debris cloud continues to expand, it interacts with the surrounding environment. Interstellar gas, dust, magnetic fields. These interactions create afterglows, radio waves, X-rays, signals that can last for months, even years, long after the initial collision has ended. This means that a single event continues to evolve, not in the center where it happened, but in the space around it. The energy disperses, the material spreads, and slowly the event fades. But it does not disappear, because the matter it created remains. The heavy elements formed during the collision do not vanish. They travel, carried through space by the expanding debris. Eventually, they mix with other material in the galaxy. Gas clouds, dust clouds, regions where new stars will form. And when those stars form, they incorporate that material. The gold, the platinum, the heavy elements, becoming part of new systems, new planets, and in some cases, new life. This is the deeper meaning of the collision. It is not just an ending. It is a beginning, a transfer from one state of the universe to another. Dead stars becoming the building blocks of something new. Violence becoming creation. And this process has been happening for billions of years, across galaxies, across time. Repeated, not constantly, but often enough to shape the universe we see today. But there is something even more profound in this, because when we look at these events, we are not just observing distant phenomena, we are observing our own origins. The elements on Earth did not all form here. They came from elsewhere, from stars, from explosions, from collisions like this. Every piece of gold, every heavy metal, was created in an environment far more extreme than anything on our planet. And then it traveled across space until it became part of something new. This connects us to these events. Not directly, not visibly, but fundamentally, because the universe is not made of isolated systems. It is connected through matter, through energy, through processes that move and transform everything over time. And neutron star collisions are one of the most powerful expressions of that connection. They take what once was and turn it into something else. They redistribute matter. They reshape galaxies. And they remind us that even the most violent events can have creative consequences. But there is still something we have not fully considered. Because while we understand the energy, while we understand the material, while we understand the signals, there is still a question. A deeper one. Why does the universe allow this? Why do these conditions exist? Why does matter behave this way? Why can something so destructive also be so essential? Because the collision of neutron stars is not just an event. It is a reflection of the laws that govern everything. And to understand that, we need to look beyond the event itself into the structure of the universe and the rules that make it possible. The collision ends, The light fades, the waves pass, and yet nothing is truly gone, because what was created in that moment does not disappear. It becomes part of something larger. When two neutron stars collide, the energy released is immense. But more important than the energy is the matter. The material ejected during the collision carries something rare, something that cannot form easily anywhere else in the universe. Heavy elements, not just slightly heavier than iron, but far beyond. Gold, platinum, uranium, elements that require extreme conditions to exist, conditions that normal stars cannot provide. Inside most stars, fusion stops at iron. Beyond that point, creating heavier elements requires more energy than it releases. The process becomes inefficient. The star cannot sustain it, which means something else must take over, something more extreme. For a long time, scientists believed that supernova explosions were responsible for creating many of these heavy elements. And while they do contribute, they are not enough to explain everything we observe. There was a gap, a missing piece in the story of where matter comes from. Neutron-star collisions fill that gap, because during the merger, conditions become so intense that a process called rapid neutron capture occurs. Neutrons are packed together at such high densities that atomic nuclei absorb them faster than they can decay. This allows elements to build up rapidly, heavier and heavier, in seconds. What would take millions of years in other environments happens almost instantly here. And when the process stabilizes, those elements remain. They are ejected into space, not trapped, not destroyed, but released, carried outward by the expanding debris cloud. And that cloud does not stay where it formed. It moves across interstellar space, mixing with gas, mixing with dust, becoming part of the material that forms new stars. And when those stars form, they inherit that material. Planets form around those stars. And those planets contain the elements created in those ancient collisions. This is how the universe recycles itself, not through gentle processes, but through events that are both destructive and creative. Neutron-star collisions are one of the most efficient ways the universe produces heavy elements. And because of that, they are directly connected to everything we see around us. The gold in jewelry, the platinum in electronics, the uranium in the Earth's crust. All of it originated somewhere. And in many cases, that origin traces back to events like this. That realization changes perspective, because it means that these distant collisions are not separate from us. They are part of the same system, the same chain of events. Matter is not static. It moves, it transforms. From stars to explosions, to clouds, to planets, to life. And neutron star mergers are one of the key transitions in that chain. But there is something else that makes this even more profound. Because these events are rare. They do not happen constantly. They require specific conditions, specific systems. Two massive stars must form together. They must both collapse into neutron stars. they must remain gravitationally bound, and then they must spiral inward over time, sometimes over billions of years. Only then does the collision occur. This means that every neutron star merger is the result of a long history. A history that began with the formation of stars, continued through their evolution, and ended in a single, brief event. But that event has consequences that last far longer, because once the heavy elements are created, they remain in circulation. They become part of galaxies, part of future systems, part of everything that forms afterward. This is why neutron star collisions matter, not just because they are powerful, but because they are essential. They provide something the universe cannot easily produce in any other way. And without them, the composition of the universe would be different. Planets would form differently. Materials would be limited. The variety we see today might not exist. This raises a deeper point. The universe is not random. Not in the sense that everything happens without structure. There are processes, cycles, events that, while rare, play critical roles. Neutron star mergers are one of those events. They act as catalysts, turning one form of matter into another, expanding the possibilities of what can exist. And because of that, they shape the universe in ways that go far beyond the moment of collision. But there is still something we have not addressed. Because while we understand the role of these events, we are still learning how often they happen, how they distribute matter, how they influence the structure of galaxies over time. This is where observation becomes important. With modern instruments, we are beginning to detect more of these events. Not just through light, but through gravitational waves. Each detection adds data. Each event provides more insight. And slowly, a clearer picture is forming. A picture of a universe that is constantly evolving, where even the most extreme events are part of a larger system. But even with this understanding, there is something that remains difficult to grasp. The scale. The idea that something happening millions of light years away can influence the composition of matter here. That connection is not immediate, not visible, but it is real. Because the universe is interconnected. Through time, through space, through the movement of matter. And neutron star collisions are one of the ways that connection is maintained. They ensure that matter does not remain locked in one place. They redistribute it, allowing new structures to form, allowing complexity to increase, allowing the universe to become more than it was before. But this leads to a final realization. Because if everything around us comes from processes like this, then we are not separate from the universe. We are part of it, built from the same events, the same transformations. And that includes the most violent ones, the ones that seem destructive. Because without them, what exists now would not exist at all. And that is what makes neutron star collisions so important. Not just as cosmic events, but as part of the story, of everything. Long before we could see these collisions, we learned how to hear them, not with sound, not through air, but through space itself. Because when two neutron stars spiral toward each other, they do something unusual. They do not just move through space, they disturb it. Every orbit, every acceleration, every shift in position creates ripples in the fabric of space-time. Gravitational waves. These waves are not like light. They are not particles. They are not energy traveling through space in the usual sense. They are changes in space itself. Imagine space not as empty, but as something that can stretch and compress. When massive objects move, especially in extreme ways, they cause that fabric to ripple outward. These ripples carry information about the motion that created them. And unlike light, they pass through everything. They are not blocked by dust, not absorbed by gas. They travel freely across vast distances, carrying with them a perfect record of the event. For a long time, these waves were only theoretical, predicted by Einstein's equations, but never directly observed. The idea was clear, but the challenge was immense. The distortions they create are incredibly small. So small that detecting them seemed almost impossible. When a gravitational wave passes through Earth, it does not shake the ground. It does not create a visible effect. Instead, it changes distances by an amount smaller than the width of a proton. And yet, we found a way to measure it. Instruments like LIGO were built to detect these changes. Long tunnels, kilometers in length, with lasers traveling back and forth, measuring distances with extreme precision. When a gravitational wave passes through, those distances change. Not by much, but enough. Enough to detect. Enough to confirm that something far away has disturbed space-time. And when the first detection happened, everything changed. Because for the first time, we were not just observing the universe through light. We were observing it through its structure, through the way space itself behaves. And neutron star collisions became one of the clearest signals. Because their motion is so extreme, their gravitational waves are strong enough to be detected across millions of light years. The signal they produce is distinctive. A rising frequency, a growing intensity, a chirp. It starts low, slow, and then accelerates, faster, stronger, until it reaches a peak and stops. That peak is the moment of collision. From that signal alone, we can learn a lot. The masses of the objects, the distance between them, the speed of their orbit, even the way they deform as they approach each other. This is something light alone cannot provide. Light shows us the aftermath. Gravitational waves show us the process. And together, they give us a complete picture. This combination of observations is known as multi-messenger astronomy. Different signals, different forms of information, all describing the same event. And neutron star mergers were the first time we saw this clearly. We detected the gravitational waves. Then we saw the light. And by combining both, we confirmed everything we had predicted. The inspiral, the merger, the kilonova, all of it. But beyond confirmation, this opens something new, a new way of exploring the universe, because now we are no longer limited to what we can see. There are events that produce little or no light, black hole mergers, for example. But they still produce gravitational waves, which means we can detect them. We can study them, even when they are invisible. This changes the scale of what we can observe. It expands our reach, because the universe is not just a visual place. It is a dynamic one, full of motion, full of interactions, and gravitational waves allow us to sense that motion directly. They are like echoes of events that happened far away, long ago, and are only reaching us now. When we detect these waves, we are not just observing. We are listening to history. Events that occurred millions or billions of years ago, encoded in the fabric of space-time and arriving here as subtle distortions. This creates a strange connection, because in that moment, we are directly linked to the event, not through light that reflects, not through images, but through the structure of space itself, the same structure we exist within. And that makes neutron star collisions even more significant. They are not just distant events. They are events that interact with the entire universe. Their influence spreads outward, touching everything, even us. But there is still more to understand. Because while gravitational waves tell us about motion, they also reveal something deeper: the limits of physics. These events occur under conditions that push our understanding to its edge. Extreme gravity, extreme density, extreme energy. And by studying the waves they produce, we can test our theories. We can see if our models hold, or if something new emerges. So far, Einstein's predictions have held, but each new detection is another test, another opportunity to learn, because the universe is not static. It continues to reveal itself. And neutron star collisions are one of the clearest ways it does that. But even with this new way of observing, there is still a question that remains. Because while we can detect these events, while we can measure them, while we can understand their physics, there is something else we need to consider. Perspective. What it means to exist in a universe where such events are possible, and what that tells us about our place within it. It is easy to focus on the collision, the moment of impact, the explosion, the light. But that moment is only a point inside something much larger. Because neutron star collisions do not happen in isolation. They occur within galaxies, within systems that are already complex, already evolving, already filled with motion and interaction. And to understand what these events truly mean, we need to step back, far enough to see the environment they exist in. A galaxy is not empty. It is not just stars scattered in space. It is a system, a vast structure made of billions of stars clouds of gas, dust, dark matter, and energy fields, all interacting over enormous distances and timescales. Within that system, stars are constantly forming. Gas clouds collapse under gravity, regions become dense, temperatures rise, and new stars are born. But the material those stars are made from is not new. It has been recycled from older stars, from explosions, from collisions, including neutron star mergers. When a collision occurs, the material ejected does not stay localized. It spreads outward, mixing with the interstellar medium. Over time, this enriched material becomes part of the next generation of star formation. This process takes time. Millions of years, sometimes longer. But it happens slowly, quietly, without any single moment that defines it. The heavy elements created in a collision begin as part of a fast-moving cloud, but as that cloud expands, it interacts with the surrounding environment. It slows, it disperses, it blends, and eventually it becomes indistinguishable from everything else. Except for one thing: its composition. Because the atoms created in that collision remain, they do not lose their identity. They do not revert to something simpler. They persist. And when they become part of a new star system, they shape it. Planets that form around that star will contain those elements. Their geology will reflect it. Their chemistry will depend on it. And in some cases, their potential for complexity may rely on it. This is the scale we rarely consider. The idea that a single event happening in a distant part of a galaxy can influence the formation of entirely new systems millions of years later. That connection is not immediate. It is delayed, but it is real because the universe is not static. It evolves through cycles: formation, destruction, reformation. And neutron star collisions are part of that cycle. They are not frequent enough to dominate the process, but they are significant enough to shape it. They introduce something new, something that would not exist otherwise. And once introduced, it spreads across the galaxy over time. But this also means something else. Because if galaxies are constantly evolving, if material is constantly being redistributed, if elements are constantly being created and reused, then no part of the universe is truly isolated. Everything is connected. Not directly, not immediately, but through processes that operate over vast distances and timescales. This changes how we think about location. The Earth is not separate from distant galaxies. It is part of the same system, the same flow of matter, the same chain of events. And that chain includes neutron star collisions, which means the elements here have histories. Histories that extend far beyond this planet, far beyond this solar system. Histories that trace back to events we are only now beginning to observe. This perspective is difficult to grasp because it operates on scales that are far beyond human experience. Distances measured in light years, times measured in millions or billions of years. But those scales are real. and the processes that occur within them are shaping everything. Even now, at this moment, somewhere in the universe, two neutron stars are orbiting each other, slowly, quietly, beginning a process that will eventually lead to another collision, another release of energy, another creation of elements. And that material will begin its own journey through space, through time, until it becomes part of something else. This continuous cycle is what makes the universe dynamic. It is not just expanding, it is transforming constantly. And neutron star collisions are one of the mechanisms that drive that transformation. But there is something else to consider, because while we can describe these processes, while we can observe them, while we can model them, we still experience them from a limited perspective. We see individual events, individual systems. We do not see the full pattern, the full structure, because that would require a view beyond our position, beyond our time. And yet, even from where we are, we can begin to understand. We can see that the universe is not random, not in the sense of being without structure. It has patterns, cycles, processes that repeat and interact. And neutron star mergers are one of those repeating processes. Rare but consistent, powerful but part of a system. And when we place them within that system, they become something more than isolated events. They become part of a larger story. A story about how matter moves, how energy transforms, and how the universe builds complexity over time. But even with this understanding, there is still something that remains difficult to answer. Because while we can describe what happens, we are still left with a deeper question. Why does the universe allow this kind of structure to exist at all? Why do these processes emerge? Why do they follow the patterns they do? And to approach that question, we need to look beyond observation, into the nature of the laws themselves. Because everything we have described depends on something deeper, something that defines how the universe behaves. And understanding that is the next step. Everything about neutron star collisions pushes us toward a limit, not a limit of distance, not a limit of time, but a limit of understanding. Because these events do not just involve extreme conditions. They exist at the edge of what our current physics can fully explain. We describe them using equations. We model them with simulations. We observe them through signals. But there is a boundary, a point where our certainty fades. And beyond that point, we begin to ask questions instead of giving answers. Neutron stars themselves already challenge our understanding. They are made of matter compressed beyond anything we can recreate. Inside them, atoms do not exist. The structure of matter changes completely. Protons and electrons merge. Neutrons dominate. But even that description may not be complete, because at such densities, new forms of matter may emerge. Exotic states, quark matter, a phase where even neutrons break apart into their fundamental components. We do not know for certain if this happens, but the possibility exists. And when two neutron stars collide, those possibilities become more important, because the conditions become even more extreme. Densities increase, temperatures rise, pressures exceed anything stable. For a brief moment, matter exists in a state we do not fully understand. And that matters, because the behavior of matter under these conditions determines the outcome of the collision. Does the merged object collapse immediately? Does it remain stable for a short time? Does it release more energy? These questions depend on physics that is not yet fully known. This is where observation becomes critical, because every neutron star merger we detect provides data, clues, signals that help us refine our understanding. Gravitational waves tell us about motion. Light tells us about energy. Together, they give us insight into the structure of the event. But they do not reveal everything. The interior remains hidden. And that hidden region is where the most extreme physics occurs. This creates a challenge, because we are trying to understand something we cannot directly observe. We rely on indirect evidence, patterns, models, simulations. And while these tools are powerful, they are not complete. This is why neutron star collisions are so important. They act as natural laboratories, environments where physics is pushed to its limits, where theories can be tested, where new phenomena may appear. Because if our understanding is incomplete, these events will reveal it. They will show us where our models fail, where our assumptions break down. And in doing so, they will guide us towards something deeper, a more complete understanding of how the universe works. But there is another layer to this, because the limits we encounter are not just about matter. They are also about gravity. Gravity, as described by general relativity, works extremely well in most situations. It explains the motion of planets, the behavior of stars, the expansion of the universe. But in extreme environments, like neutron star mergers, we test it at its limits. Strong gravity, rapid motion, high energy, conditions where even small deviations would become noticeable. So far, our observations match our predictions. But each new event is another test, another opportunity to see if something unexpected appears. And that possibility is important, because it suggests that our understanding may still evolve, that there may be deeper layers to physics waiting to be discovered. Neutron star collisions bring us closer to those layers. They allow us to explore regimes that cannot be recreated on Earth. They provide access to conditions that only exist naturally in the universe, and by studying them, we expand the boundaries of what we know. But this also leads to a more philosophical question. Because when we reach the limits of understanding, what does that mean? Does it mean the universe is too complex, too vast, too detailed? Or does it mean that we are still learning? That our current models are just approximations of something deeper. Neutron star collisions do not answer that question directly, but they highlight it. They show us where the edges are, where explanation becomes uncertainty, and where curiosity begins. This is not a failure of science. It is its purpose: to identify what we know and what we do not, and to move forward from there. Because every limit we encounter is also an opportunity to refine our theories, to improve our observations, to ask better questions. And neutron star mergers provide many of those opportunities. They challenge us, not by being inaccessible, but by being just within reach, close enough to observe, complex enough to question. And that balance is what makes them so valuable. But even with all of this, there is still one final perspective to consider. Because while we study these events, while we analyze their physics, while we try to understand their structure, we are still observing them from within the universe, from a specific point, a specific time. And that perspective shapes what we see, which means there may be more connections, more patterns, more structures that we have not yet recognized. And to approach that idea, we need to step even further back, beyond individual events, beyond galaxies, into the broader structure of the universe itself. Because neutron star collisions are not just isolated phenomena. They are part of something larger, something that connects all of it together. When we look at a single event, a collision, an explosion, a flash of light, it feels isolated, contained, like something that happens and then ends. But the universe does not work that way. Nothing is truly isolated. Every event exists within something larger, and that larger structure is always changing. The universe is not still. It is not a fixed background where events happen. It is dynamic, expanding, evolving over time. Galaxies are not stationary. They move. Clusters shift, structures grow. And on the larger scales, everything is drifting apart. The expansion of the universe stretches space itself, increasing the distance between galaxies over time. This expansion is not something we feel directly, but it defines the environment in which all cosmic events occur. Neutron star collisions happen within this expanding framework, which means their effects are not just local. They are carried into a universe that is constantly changing. The material ejected from a collision begins its journey in one region of space, but as time passes, that region itself moves, expands, and evolves. The debris does not remain where it started. It becomes part of a moving system. And that system is part of something even larger. Galaxies are not evenly distributed. They form patterns, filaments, clusters, voids. Together, these structures create what is known as the cosmic web, a vast network of matter stretching across the universe. Within this web, galaxies are connected, not physically in the way we connect objects, but through gravitational influence and shared motion. And within those galaxies, events like neutron star mergers occur, which means that the products of those events are injected into this larger structure. Heavy elements created in a collision do not remain confined to a single star system. Over time, they become part of the galaxy's interstellar medium, and from there, they can spread even further, across regions, across structures, becoming part of the cosmic web itself. This changes how we think about scale, because an event that begins in one location can influence matter across vast distances, not instantly, but over time. And time is something the universe has in abundance. Billions of years, enough for material to move, to mix, to become part of entirely different systems. This is why the universe appears both structured and uniform. Structured on large scales, uniform in composition, because the processes that create matter also distribute it. Neutron star collisions contribute to that distribution. They are not the only mechanism, but they are one of the most important for heavy elements. And because of that, they play a role in shaping the chemical makeup of the universe, not just in one place, but everywhere. This creates a subtle connection, a connection between distant regions of space, a connection between events separated by millions of light years. Because the material created in one place can eventually become part of another. This is not immediate. It does not happen on human timescales, but it happens. And when we step back far enough, we begin to see the pattern. A universe that is constantly redistributing its contents, recycling matter, transforming it, moving it through different states. Stars, explosions, clouds, new stars. And neutron star mergers are one of the key transitions in that cycle. They convert one form of matter into another, and then release it into the larger system. But there is something else that emerges from this perspective. Because while the universe is expanding, while structures are moving apart, local systems remain connected. Galaxies hold together. Clusters remain bound. Which means that even within an expanding universe, there are regions of stability. Regions where processes can repeat, where cycles can continue. And within those regions, events like neutron star collisions continue to occur. This creates layers of behavior, local stability, global expansion, processes that operate at different scales but interact with each other. And neutron star mergers exist within both. They are local events with global consequences. They occur in specific systems but contribute to the overall structure of the universe. This dual nature is what makes them so significant. They connect scales, from the smallest interactions of particles to the largest structures in existence. But even with this understanding, there is still a deeper question. Because while we can describe how matter moves, how energy spreads, how structures evolve, we are still left with something fundamental. Why does the universe have this structure at all? Why do these patterns emerge? Why do these processes repeat? Why does matter behave in a way that allows complexity to grow? Neutron star collisions do not answer these questions directly, but they are part of the system that makes them possible. They show us that the universe is not random in the way we often imagine. It has rules, patterns, processes that build upon each other. And those processes create the environment we observe. But even that may not be the final layer, because beyond structure, beyond motion, beyond matter itself, there may be something deeper, something that defines why the universe behaves the way it does. And to approach that idea, we need to take one final step back, to look not just at what happens, but at what it means. The collision ends, the light fades, the waves pass through space and continue on, far beyond where they began. And after everything, there is silence again, not because nothing happened, but because everything that could happen already did. Two neutron stars, objects that once were stars, collapsed remnants of something much larger, have completed their final act. They no longer exist as they were. Their identities are gone, their structure transformed. And yet nothing was lost. Because in the universe, nothing simply disappears. It changes. That is the pattern we keep returning to. Not destruction, transformation. Over and over again, at every scale. Stars are born, they evolve, they collapse. Their remnants interact, collide, transform again. And through those transformations, something new is created. Not immediately recognizable, not always connected in an obvious way, but part of the same continuous process. Neutron star collisions are one of the clearest examples of this. They take something that has already reached the end of its life and turn it into something else entirely. Not by preserving it, but by breaking it apart and redistributing it. This idea challenges how we think about endings, because what appears to be an end is often just a transition, a movement from one state to another. The neutron stars do not survive the collision, but their matter does. It spreads, becomes part of the galaxy, part of future systems, and eventually part of everything that forms afterward. This includes planets, worlds that may one day support complex structures, environments where chemistry becomes more intricate, and in some cases, conditions where life can emerge. That connection is not immediate. It spans millions, even billions of years. But it exists because the universe is not a collection of separate events. It is a network, a system where everything is linked through time and transformation. This perspective changes how we see ourselves, because the elements that make up our world did not originate here. They were created elsewhere, in stars, in explosions, in collisions like the ones we have been exploring. This is not just a poetic idea. It is a physical reality. The atoms around us carry histories that extend far beyond Earth, far beyond the solar system. histories that trace back to events we are only now beginning to observe. And those events are not rare in the sense of being unique. They are rare in frequency, but common enough to shape the universe. This creates a balance between stability and change, between structure and transformation. The universe does not remain static, but it does not dissolve into chaos either. It evolves, guided by the laws that define how matter and energy behave. Neutron star collisions are one of the ways those laws express themselves. They show us what happens when gravity, density, and motion reach their extremes. They reveal the boundaries of what is possible, and in doing so, they expand our understanding. But there is something else that emerges from this, because when we observe these events, we are not just studying distant objects. We are observing processes that are fundamental to the universe itself, processes that have shaped everything we see, and that continue to shape it. Even now, somewhere in the universe, two neutron stars are orbiting each other, slowly, quietly, beginning a process that will eventually lead to another collision, another transformation, another release of energy and matter. And that cycle will continue, not endlessly, but for as long as the conditions allow it, because the universe itself is evolving. Stars are forming, galaxies are changing. The large-scale structure continues to develop, and within that structure, events like these play a role that is not always visible, but always present. This leads to a deeper realization, because while we can observe the universe, while we can measure it, while we can build models and theories, we are still part of it. We are not separate observers. We exist within the same system, made from the same matter, governed by the same laws, which means that understanding the universe is also a way of understanding ourselves, not in a personal sense, but in a fundamental one. Because everything we are, everything around us, is the result of processes like these, processes that operate on scales far beyond our experience, but ultimately shape the reality we live in. This does not make neutron star collisions less distant, but it makes them more relevant, because they are not just events that happen somewhere else. They are part of the same chain of transformations that led to everything we know. And that chain continues. Even as we observe it, even as we try to understand it, the universe does not pause. It does not wait. It continues to evolve. And within that evolution, there will always be moments where matter is pushed to its limits, where structures break, where new forms emerge, and where the boundaries of understanding are tested. Neutron star collisions are one of those moments, not because they are unique, but because they reveal something essential, that the universe is not defined by permanence, but by change, a continuous process of transformation from one state to another. And in that process, nothing is truly lost. It is only rearranged, reused, reimagined in forms that will continue to evolve, long after the collision is over, long after the light has faded, long after the waves have passed, because what remains is not the event itself, but its influence. And that influence is everywhere.